Hello, everyone. Thanks, Maria, for the introduction. This is another paper with a long title, PRM-RL, Long-Range Robotic Navigation Task by Combining Reinforcement Learning and Sampling-Based Planning. This is my grandmother with my cousins and me. If you guys are wondering, I'm the one in the middle. She was a wonderful grandmother, but she was born with a mobility impairment. And walking to a grocery store or to a park, it was excruciating for her. And she's not alone. In US alone, there's 11 million people that cannot leave their homes without some sort of assistive technology. And service robotics, robots that navigate long distances to provide services, to bring packages and deliveries, can help improve independence for people like my grandmother, and at the same time, open new opportunities for the rest of us to enjoy. Imagine many different robots doing many different tasks for all of us in complex environments like this one. There's outdoor spaces, there are indoor spaces, long distances to cover. So for that reality, we need two things. We need autonomy, which means that we need robots that can autonomously navigate long distances while performing specific tasks. On the ground and in the air. Second, we need to be able to easily adapt to new environments. Because there are millions of people, countless environments, we want to be able to deploy these robots easily from the information that's already available to them. So how do we achieve this easy-to-adapt autonomy? We do that by combining learning and long-range planning. We train robots to do a specific task, and then use sampling-based planning to extend the reach of the trained agents. So let's talk about reinforcement learning. Reinforcement learning is a technique that helps robots learn behaviors. Behaviors in this case are policies which map observations from the world into actions that the robot performs. Robot learns these behaviors and policies by interacting with the environment, observing how the world changes to their actions, receiving a numeric reward, and the learned policy learns to maximize the expected discounted cumulative reward that the agent occurs along the way. They are really good at reinforcement learning policies are really good at mapping raw sensor inputs, such as images or LiDARs in these manipulation tasks, to the actions that the robot can perform. They're also really good at learning tasks and robot dynamics, such as the helicopter control or our prior work on the UAVs with the suspended load delivery. However, they often lack context and the knowledge, full observability of the space that is needed for the long-range navigation. On the other hand, we have sampling-based planners. They're made to handle long-range navigation. They approximate the space of all possible robot motions. Now, that sounds complex, but actually they do that by sampling all the poses and connecting them with the small, feasible robot transitions that create data structure that captures valid motions of the robots in a large space. However, one of the most expensive steps in that process is constructing the transitions between the sample poses. So the most feasible way to do that is just simply not to consider robot dynamics, and the sampling-based planners, like probabilistic roadmaps or PRMs, that create reusable roadmaps for planning often do not consider dynamics. But for our application of the long-range navigation, PRMs are the tool to do that. They're suitable for our application because we want reusable maps. We want to put a robot in the environment once and reuse it many times. So let's see how PRMs are built. They work in two phases. First, we sample the samples randomly in the space, and we reject those that are in collision. Then using a local planner that's given, it's typically straight line planner, we try to connect each node with its nearest neighbors. And we keep the edges that are valid, that are collision free. and reject the other ones. So when it's time to query a new map, we add our start and a goal. They're added to the map using the same method. And then the search algorithm goes and finds the shortest path between start and a goal. So to execute the motion over the path, we typically use another method like reinforcement learning or artificial potential fields to generate a trajectory that follows the straight line planner's path. The problem with that is that the straight line planner is not always executable for a given robot and might not satisfy the task constraints. So unlike the traditional local planners, our planner can account for inaccuracy stemming from the sensor and localization noise. So let's see how we develop PRM. Let's see how does PRM work to enable service robotics, where a robot is trained once for a task and easily adapted to perform long-range navigation in different environments. First, we train with reinforcement learning, a local planner policy for a specific robot to perform specific task. In the example on the indoor navigation task, that is a short-range policy that avoids obstacles. This task is independent from the environment where the robot is going to be deployed or going to be operating. So different robots have different sensors. The sensors have different accuracies and so on, different error levels. Regardless, that behavior can be learned once for a particular robot. So next, to prepare the robot to work in a specific environment, we use floor plans to build PRMs with respect to our reinforcement learning agent as a local planner. The floor plans are readily available, and the same floor plans can be used for many different robots or that we wish to deploy in that environment. This is a one-time robot environment setup. So to build the PRM-RL, we sample the floor plans and retain collision-free samples just like we do with the standard PRMs. However, we connect two nodes only if the reinforcement learning policy can consistently navigate between the two nodes. So we attempt the connection n number of times and only retain edges that have where the success rate is above a certain threshold. So this way, the resulting roadmap is tuned for the noise and the abilities of the particular robot, not only its geometry. For example, nodes near walls will not be included, and the obstacles are likely to be, and they're going to be less likely to be connected to the roadmap. The roadmaps in the same environment for the robots with the same geometry but different abilities or different sensors, they're going to look differently. The connectivity is going to be different. So the querying phase is the same as in PRM, although we can also test other trajectory metrics such as minimal energy consumption or shortest time, etc., which is not generally available with the geometry-based approaches. So at the execution time, the reinforcement learning agent navigates to the first waypoint. Once the agent is close enough to the waypoint, the next waypoint becomes its new goal, and it continues progressing that way. Note that this step adds additional error source or potential failure because the agent never reaches the waypoint, but that really happens in reality because we don't have perfect localization. So let's see how we train our indoor navigation agent. Our robot is differential drive mobile platform. The agent is trained in small environment, and it's rewarded for obstacle avoidance and when the goal is reached. The observations are noisy, one-dimensional LiDAR observations. We see them there. They are noisy. And the only thing that the robot gets is that basically it tells the black thing means that the obstacle is closed, the white means that there is no obstacle nearby. And we assume perfect localization here in terms that we have the coordinates of the goal on the robot. The actions are wheel velocities. There is no controller underneath, commanded at 10 Hertz. We train it with the DDPG agent, which takes Actor network is 2 hidden fully connected layers, and a critic that has state embedding plus the 2 hidden layers. This is not a simple task. It connects full sensor, very noisy observation, very little information observing the environment to the full controls. And it is a one-time cost per task per robot. So let's see what that agent looks like. It has about 82% success rate for goals within 10 meters. It sometimes, is it playing? Yeah. So sometimes it can go around the corners, but sometimes it goes further along. So we evaluate the method in the same with the same trained RL agent and build roadmaps using the floor maps in 3 other office buildings. These buildings are 60 times larger than the environment where the agent is trained. We use 20 trials per edge, and we expect at least 85% success rate. So this is the visualization of building the roadmaps. We see that the edges are added even though there is no clear line of sight, and that the nodes that are near the agent are not, that are near the walls are not usually added to the roadmap. The largest roadmap contains 1,700 nodes, 60,000 edges, and require 23 million collision checks to perform. Again, it is a one-time setup for the environment. So to evaluate the roadmaps, we ran 100 queries in the 3 environments plus the training environment. So in each of the environments, same start and goal. We compare with the PRMs with the straight line planner. Each task, so start and goal, are reachable in both roadmaps. And we look at the success rate. We see that the PRM-RL is about 2 to 3 times higher success rate than the baseline method. That is because the nodes were positioned and connected to be more appropriate to the robot's capabilities and shortcomings, to overcome the shortcomings. And recall that we added additional sensor and an effector noise, which explains why the low overall completion rate. We also looked at how many waypoints the agent successfully navigates through, and PRM-RL is about twice as successful, goes further, makes twice as many successful transitions, and the trajectories that it produces are about twice as long. So let's look how that agent looks like. So the longest trajectory here is 215 meters. We here see in the upper left corner the LiDAR observations that the robot sees. The wobbling that it sees is due to the added noise sensor and an effector noise. We see it navigating here in other environments. Sometimes it almost gets in collision, but it recovers. We also applied the agent to the aerial cargo delivery task. The task here is to navigate long distances while carrying a suspended load and putting a constraint of the maximum displacement of the road. The difficulty here is the task dynamics, and we see what it looks like when we don't control for the load. This is not what we want. So for this case, we used the pre-trained continuous action fitted value iteration agent, which was trained in a small environment, 1 meter hypercube around the goal, and the goal was to minimize residual oscillations. And you can see what the trained agent looks like. This agent has Lyapunov stability guarantees, which means that we have the guarantee that the agent is going to reach the goal. So to evaluate it, let me see, no. There was going to be a video, but it's not playing. So we evaluated the agent in 3 environments, 2 experimental, 1 in simulation. The 2 experimental environments required 10 degrees of the displacement, and the transfers from the simulation to the robot directly. The simulation, the simulation environment is a simulation of a city that is 60 million times larger than the trained environment, and the robot navigates trajectories over 1 kilometer there. Yeah, there's not this video. Oh, yeah. So PRMRL allows learning robot tasks independently from the environment of the deployment. And with one-time setup, they build roadmaps tailored to the particular task and robot. We developed an end-to-end navigation RL agent and demonstrated the method on 2 different tasks, both in simulation and experimentally. Overall, the PRM-RL is a step towards an easy-to-use autonomy, where a future where maybe different robots perform different services for all of us. And thanks to my collaborators, and we're going to be in T6.